Hello. Now we are going to apply Lagrangian equation of motion to some uh, simple fundamental system such as a linear harmonic oscillator and simple pendulum. First, we need to apply Lagrangian equation of motion to linear harmonic oscillator. This is an example of linear harmonic oscillator. One simplest system I am taking, that is the spring mass system. Here our object is to find the equation of motion of a spring mass system by using Lagrangian method. Okay, then obtain the time period of the motion. So this is ideal spring mass system consists of a massless spring. One of its end is connected to a mass and the other end is to connected to rigid support. Here this is ideal case. We consider that the spring mass system lies on a frictionless horizontal surface. So this is our spring mass system. If you consider uh, this is one rigid system, this is our spring. Okay, other end is hang by mass. Okay, if a force is applied on the mass to stretch or compress the spring, then release. The motion of the system is simple harmonic motion. If x is a displacement of mass m at any instant, then the restoring force extracted by the spring on the mass is we can write F equal to minus kx. Okay, restoring force F equal to minus kx. We know kinetic energy k equal to 1 by 2 mv square already. So here the kinetic energy of the system, we are going to write letter T, kinetic energy 1 divided by 2 mv square. So these are our known two quantities. This is restoring force. By using this restoring force, we can derive potential energy. Here the K is the force constant. The potential energy of system at displacement x is, we can write potential energy can be expressed in terms of force can be expressed in terms of potential energy, right? Or else I'm going some fundamental way. V equal to minus integral 0 to x to boundary conditions. Okay, this is initial boundary condition x equal to 0. After applying force, its mass is displaced, instant is displaced somewhere here. Okay, somewhere here. This is x equal to some x position. We don't know. Here I am going to use this is x position. This is x equal to 0. Okay, or else leave it this is boundary condition 0. This one is boundary condition 1 0. This is x boundary condition. So initial boundary condition 0, the final boundary condition is x. force into dx. So we know force minus kx, right? V equal to minus integral 0 to x kx dx. So therefore V equal to 1 divided by 2 kx square. This is our potential energy of spring mass system. This is our kinetic energy. Okay. Now we are going to apply Lagrangian, not Lagrangian equation. First we need to take Lagrangian. So one more important factor here. Here we need to use generalized coordinates, not V, right? So therefore I'm going to write this kinetic energy T equal to 1 divided by 2 m mass x dash, which means velocity square. Okay. Then the Lagrangian L of our system, L equal to T minus V. Lagrangian, not Lagrangian equation. Okay. First we need to take Lagrangian. So Lagrangian L is equal to, what is kinetic energy? 1 divided by 2 m x dot square minus 1 divided by 2 k x square. Now we need to apply the Lagrangian equation. We know Lagrangian equation d by dt of partial derivative of L Lagrangian. Here the variable is x dot minus dou L divided by dou x equal to 0. Then simply substitute this L value here. So for that I'm going to derive this one, dou L divided by dou x, first one. So if you look at this term, this one is 0, this one is minus, here x 2x, right? So 2 gets cancelled, I got kx. Next, partial derivative of L divided by x dot. Here the second term is going to 0. This one, m, is constant, x square to x, 2 gets cancelled, remaining I got a x dot. So simply I'm going to substitute these two factors here. Okay, these two factors here I'm going to substitute. So d by dt dou L divided by dou x dot, I think m x dot minus dou L divided by dou x minus kx minus to minus plus kx equal to 0. So this is, here d by dt is there, then we need to write this one, m x double dash plus kx equal to 0. So this is our Lagrangian equation of motion of spring pendulum. From this equation, we can write it like this also, x double derivative k divided by m x equal to 0. This is also equation of motion of spring pendulum. So this is the derived equation of motion of spring mass system. This represents a simple harmonic motion whose time period is given by this one. Time period t equal to this is time period t equal to 2 pi root m divided by k. So this is our time period of simple harmonic motion. So this is our equation of motion. Next class we are going to discuss simple bending.